Welcome back to the classroom. My name is Mr. Wong, and today we're going to be talking about Module 4, Electricity and Magnetism, with a focus on Inquiry Question 1, Electrostatics. I'm going to go through the last dot point, which is to analyze the effects of a moving charge in an electric field, relate that to potential energy, and also equipotential lines. So what you will need to know today is, understand what we mean by the definition of electric potential and potential difference. We're going to analyze the behavior of a charge moving through an electric field. The page references that you'll need are these from your textbook if you want additional reading, and let's go. Alright, so potential energy refers to store energy. You already heard about that before. We talked about gravitational potential, which is the energy that's used to work or to do work from a gravitational field. We also talked about electric potential, so energy that can be used in a chemical reaction. And then the next one we have is electric potential. Okay, so what we define in physics as electric potential energy is the energy that's needed to move a charge against an electric field. Essentially what that means is if we have a positive charge here, it's saying that what energy does this particular charge here have according to the movement of the electric field to then move to the negative side of the plate. So how much energy can this positive charge store up if I move it closer to this positive plate here to when I release it, that it will be repelled by this positive charge and it will be moving towards this side of the field. So let's just quickly talk about electric potential. So imagine I have a positive charge next to a negative plate. Now, as soon as I put a positive charge near a negative plate or negative field, it's going to try and move straight into this field here. So in terms of the kinetic energy, there's a lot of kinetic energy dragging it towards the plate, okay? But there's not much, so there's a high amount of kinetic energy, but there's not much electric potential energy here. Swap it around, say we have a positive charge that is really close to a positive plate. Now, based on what we know from electrostatic forces, they don't want to be near each other. So when I put a positive charge near a positive plate, the positive plate will really want to push this charge away from it. And in this case, there is a lot of electric potential energy here because the electric field of the positive plate, there's a lot to do here that will want to push this positive charge away. So think about it this way. The more the electric field wants to push the charged particle away, the higher the potential energy. Okay, so let me perhaps write that down. Okay, so I'll write it down here. So the more the electric field wants to move a charge away, this is the key point, away from itself, means the charge has a greater electric potential. So the energy to be pushed away from the electric field. That's the key point. Alright, let's go through these multiple choice questions. So we have a 6-volt battery. Get my laser pointer back. And it's connected to 2 parallel plates. Okay, X, Y, and Z are positioned between these plates here. Which statement is correct? A, B, C, or D? Quickly pause this here if you want to sort of critically think about it. I'm going to go through the answer now. So 1A is A. So X and Y have the same electric potential. So If you're thinking about it here, if they're both positive charges, then from this side of the plate, they're equally distanced away from both sides. Okay. Question B: what is the direction of electric field at Y? Okay. The answer here is C, top of the plate to the bottom of the plate. The reason being, you need to look at this electric circuit construction here. Okay, this long end is generally the positive side, and this end, the shorter end, is the negative side, which means that this will create a negative plate here, and this will make a positive plate here, which means that the electric field will always go positive to negative, so it goes down like so. So that's why it goes from top to bottom. Right, let's get into the nitty-gritties of this dot point here, and that is to analyze the effects of a moving charge in an electric field. So we know different types of electric fields. We've talked about it. We talked about the point charge. We talked about the dipoles. We talked about the charge plates. So when we talk about equipotential lines, imagine they're like contour lines when we're looking at a topographic graph. All right, so where the lines are surrounding, or where the lines are present, it means that the altitude for this topographic graph is, the same. So it's at the same height. Similar idea when we're looking at equipotential points of electric fields and magnetic fields in that case. Where we draw those lines, it means that the electric field strength is the same. In the case of a point charge, remember, the electric field moves in all directions, giving that sort of circular form to it. Which means if I draw a circle with the same radius around the point charge, wherever I go, the potential, the electric potential of that particular component, or the electric field of that component, is and should be the same. So if we have a look, obviously the potential is strongest near the charge, and you can see it goes lower as we go away. If I draw out the line here, this represents that the electric field strength is, or the electric potential is 15.6 negative, because it's a negative charge, and this is 6.1 there. You can see there's that difference there. The further away I am from the electric field, the electric potential is smaller, while as if I'm closer to the field, the electric potential is a lot stronger or a lot higher, which makes sense because if I have a negative charge, it's going to want to move further away from this negative charge here. So that's what I mean by equipotential points, where a specific part of the electric field has the same value. Alright, so what that means is at this particular point, the difference in potential, so if I am, for example, a particle at this position and this position, if I try to calculate the difference in electric potential, that would be 0, because they're equally distanced away from the charged particle. Okay, if I move the charge from here to here, then there is a specific value for that change. And this potential difference is also what we know as voltage. Okay, so when we talk about voltage, it's actually potential difference, the difference in electric potential of a charged particle once it's moved around an electric field. Okay, why do we use these lines? Well, firstly, it helps illustrate where the potential is constant. And don't forget, these lines must be perpendicular to the field when we draw it. So you can sort of see they're cutting at a perpendicular angle to these lines. Okay, the next bit is working out the type of kinetic energy that a charge will experience when you move it through an electric field. similar to an object that is going through a gravitational field. If a mass object is falling due to gravity, it's gaining more kinetic energy. Same idea applies if it's a charged particle moving through a electric field. So as this goes down, the potential energy, the gravitational potential energy goes down, this kinetic energy will go up. Same idea here, the electric potential is going to go down, and then also the kinetic energy is going to go up. Okay, so let's try and derive an equation that can sort of explain how it all works. Okay, so the gravitational formula is U equals mgh. Okay, UG meaning by the gravitational potential energy. If we look at it in terms of the work done formula, for this, we know that work done is force times displacement. In this case, that means the change in height. So the change in height from here to here, that's the displacement that we're looking at in terms of the work being done by gravity in this case. So when it comes to the expression of the change in gravitational potential, we can say that as the object is coming down, it's losing gravitational potential. So you can see that the gravitational potential is a negative number, okay, because we're losing gravitational potential energy in order to gain more kinetic energy. So whatever we lose in GPE, that's being gained as kinetic energy. And this is quite important because this is the same point we make when we're talking about a charged particle being pushed away by the electric field. Okay, so let's look at the electric field example here. So we know the force exerted by an electric field is F equals EQ. Right, E is the electric field strength, Q is the charge of the particle we're looking at. When we look at the work done, it's force times displacement. So we know that force is given by this equation here, so we just sub that in. So EQD, that's self-explanatory there. So the change in electric potential energy can be expressed as the negative work done. Okay, what that means is the electric field is putting in the work to move this object away from the electric field. So we're using energy to move it away. So we can express the electric potential. In this case, same idea here. A change in electric potential, or the negative change in electric potential, equals to greater kinetic energy. So again, in this case, the more electric potential energy I lose, that is being converted into the kinetic energy of the charged particle. Okay? So when we talk about potential difference, we're saying that it's lost potential energy. That's essentially what voltage is. Okay? So electric potential is the energy that's needed to move a charge against an electric field. The electric potential V is defined as the potential energy per unit charge. This is what we have here. However, generally it's actually quite difficult to measure the actual potential energy of a given particle at a given point in the electric field. So it tends to be a lot easier to measure the potential difference rather than the potential itself. And so we rewrite it like this. Okay? So we're saying that the potential difference is equal to the change in potential energy divided by the charge. Alright, so that's how we define voltage, basically. So this is the wording we call voltage. It's also known as potential difference. But we also know this as the change in electric potential energy divided by the charge. Alright, so that's what we talk about in terms of voltage, is that sort of difference in energy. Alright, so this is the formula that you'll need to remember. This is also given to you on the formula sheet. Potential difference measures the difference in two electric potential points. It's also defined as the work required per unit charge to move a positive charge from infinity to a place in the electric field. So any position to some kind of position within this electric field, it'll have a potential difference. Okay, so that's what we mean there. Alright, so let's go through some calculations, and then that will wrap up the lesson for today. So question A, or 1A, it says calculate the potential difference between 2 point charges. So potential difference is V. Let's firstly work out what we're dealing with here. We have energy. So the electric potential energy of the charge changes by this value here. So in this case, that's delta U. Our charge here is Q. So delta U over Q, that's our value there. Okay, let's grab the calculator out and go through. So my value here is a voltage of 200. Okay, so that's the difference that I'm seeing there. The next bit I need to do is calculate the change in potential energy. So calculate the change in potential energy if the charge was that instead. Okay, so I know that the potential difference is 200. I want to find the change in potential energy. And I know that the charge is 7.6 times 10 to the power 2. So rearrange that, 200 times 7.6 power 2, negative 2, sorry. And so the answer we get in this case is 15.2 joules. Okay, so that's what we have. Pretty sure that's correct. Okay, so that's what we have there. Did I write joules? Yes, I did. Okay, sweet. The next one I want to really challenge you is, given that the formula for work done is this equation here, could you try and demonstrate how these two formulas would give us this equation here? So the electric field strength is change in voltage, or change in voltage, or change in potential, or the potential difference, sorry, divided by distance. Okay. If you want to have a go, pause it here because I'm going to quickly show and tell, and then we'll go to the final question. Alright, so I know that work is force times distance. Now I know that I can rearrange that equation using this equation here to say that the charge times the electric field times the distance is the work done I'm looking for. Okay. I also know that the change in potential, or the voltage, is given as the work done divided by charge. So if I rearrange that, then work is equal to change in electric potential, or voltage, time charge. So I can rearrange and do delta V times Q equals to QED Okay, so I know that the charges are the same, so it's the same charge going through the electric field, cancel them out. E, making it the head of the subject, will give me this particular equation here. So that's how you derive it. In terms of units, because this is obviously voltage, so that's volts, divided by distance, which is measured in meters, so that's volts per a meter. That's the units we're talking about here. Now this equation I have here demonstrates a negative sign. So what can that tell us in terms of the electric field and the electric potential? Let's quickly go over that. And that's your working out there. The reason being is assuming if we have a positive charge that's moving at rest in the electric field, it's going to accelerate in the direction of the electric field. So if it's positive charge, it's going to go to the negative charge. So it's going to go to the opposite of where the positive side is from. Okay, so from conservation of energy, this kinetic energy must come from somewhere. So when we move something, it has kinetic energy. So it comes from a decrease in electric potential. So maybe I'll just write that down, electric potential. Hence, delta V is negative, okay, because that represents a drop in potential energy. So this negative represents a drop in the electrical potential energy. Right, the last one is we have a pair of charge, or we have a pair of parallel charge plates with a potential difference of 220. So that's delta V. Positive charge of magnitude of this, so that's positive. Which of the plate is positive? If we quickly look, again, I'll do a quick little scribble. The shorter side of the battery is always negative, the longer side is always positive. So this part, the top part is positive, the bottom part is negative. Which will the charge, or what will the charge do if it's free to move? Now the charged particle, because it's positive, it's going to go to the negative plate. Or not like that, but more specifically, just straight down. How much work will be done on the charge? Okay, so we know that the potential difference is due to the work over charge. So the work done is potential difference times the charge. In this case, it's 220 times 2.6 times 10 to the power of 8. And that's going to be your answer. Because it's work done, it's in joules. So you do that. So in this case, that's 5.2 10 to the power of 6 joules. Alright, that kind of concludes our lesson for today. So we looked at work done and conservation of energies from electric potential to kinetic energy when a charged particle is going through an electric field. We talked about what electric potential is, and we looked at how electric potential energy and voltage, which is potential difference, are related to each other. If there's anything you didn't quite get during this video, please replay it and go back to certain points that you need. If not, please join me in the next lesson, and hope you enjoyed the video.